Okay, so in the next 75 minutes, so what I want to talk about is some new methods in understanding dynamical systems on three manifolds. So we are given a closed three manifold, and we have a vector field giving on it which does not vanish anywhere. And what we want to try to understand, what is this resonance? Yeah, well, there's nothing to be adjusted here. Okay, good. So, okay, so somebody switch it off this stuff. Okay, so what one would like to understand is the orbit structure of such a system. And here orbits, I just refer to the unparameterized integral curves. And of course, 3 dimensions can be already quite complicated. And people thought about it, how can one sort of get a handle on it? And of course, since we are talking about one-dimensional orbits, it would be very nice if we could reduce the problem to 2 dimensions. Now that is a brilliant idea, which unfortunately most of the time doesn't work. But nevertheless, let me just give the concept, which is actually a special case of a more general concept, which works, as it turns out, for many dynamical systems. So, namely, what one tries to do, and this idea goes at least back to Poincaré, is to try to find a global surface of section. So a global surface of section is a closed 2-dimensional submanifold, a compact 2-dimensional submanifold. It might have boundary components, but if there's a boundary, then the boundary components consist of periodic orbits. Are periodic orbits. And then the surface itself has a property that the interior of the surface is transversal to the flow, and now a global property, namely, if we start on the surface, we return in forward time back to the, if we start on the interior of the surface, we return to it back in forward time. So if we start on the interior of the surface, the flow line hits it in forward time. Forward time. So now, that of course has now the advantage that we can actually define a return map, and then the dynamics would be sort of encoded in this. So that is a nice idea. It sometimes worked. So, for example, Birkhoff used it. But in general, there need not to be such a thing. So now, let me give you a sort of overdoing example. Namely, on S3, we know that there are, let's assume we are on S3. Then if I have a global, and I have a dynamical system on S3, if I have a global surface of section, it must have a boundary, because otherwise you could transport it around by the flow, and the 3 sphere would fiber over S1, which would tell you pi 1 would be non-trivial. So there has to be a boundary component. Now, however, if I give you now a dynamical system which doesn't have any periodic orbits, it couldn't have such a surface of section, and we know that there are smooth, even real analytic, nowhere vanishing vector fields, by example of Kuperberg, which do not have any periodic orbits. So something of this type need not exist, and soon the class also. So maybe asking for this in general for theory is not such a good question. So the art of asking questions here, what are the good questions? Now, the question is, so it might be, for example, that if we, so first of all, surface of section might be not the good concept, but maybe there's a better concept above, and surface of section is just a particular case of it. Maybe. We will see that's true, but not for all dynamical systems, so maybe we have to be a little bit restrictive about the dynamical system. So arbitrary vector field doesn't work. Now it turns out volume-preserving vector fields is a more restrictive class, but also there are at least C1 examples without periodic orbits. So on S3 it would be also out. However, it turns out that now already it gets hard to imagine what is there besides volume-preserving vector fields if we don't want to go so far that we actually give very precise classes of very precise vector fields that we know, of course, it's sort of difficult to generate them. So it turns out that during the last 20 years, some feeling has developed what kind of vector fields can be handled, and it's a surprisingly large class. So let me just give you the condition, and then I tell you what it roughly speaking means geometrically. Now the condition is the following. You should consider vector fields X which have the property that there is a one form with the property that lambda eventually lambda is a volume form, and then this, so vector field, so that there is such a one form, so that lambda on X, say, is positive, and d lambda contracted by this vector field vanishes. Then, of course, when I study the orbit structure and I multiply a vector field by a positive function, the orbit structure wouldn't change. I'm not interested in the particular parameterization, so I might say this equals 1, and these are called Reb vector fields. So now that looks like an awfully strong condition, but so there are, in fact, quite a number of these vector fields. For example, if you take any Riemannian metric on a closed surface and look at the geodesic flow and restrict it to the unit sphere bundle, it has this property. So geodesic flows are particular examples of this. So now, so what does it geometrically mean? It means the following. In dimension 3, a volume-preserving flow in dimension 3 may be viewed as a Hamiltonian flow restricted to an energy surface. And now this condition means that you can find a symplectic four manifold, realize this as an energy surface, and foliate the neighborhood by energy surfaces which have a flow on it which is conformally symplectic to this one. So it's some kind of stability condition. You have a flow which you consider as a Hamiltonian flow, and then you can find a Hamiltonian system so that the closed by energy surface precisely have the same flow on it. That is precisely what this condition means. Some kind of a stability condition. So now, as it turns out, this condition here makes it possible to relate the study of this dynamical system completely equivalent to understanding, as far as our aim is concerned, to reducing the three-dimensional problem to a two-dimensional problem. It makes it equivalent to problems of studying holomorphic curves. So let's look a little bit at the structure what we have here. So we start with such a one form. Let me give you first an example. So look at the units here in C2, and let me write the coordinates here as Q plus IP. And then there is the standard example of such a form, which is 1/2 Q dot dP minus P dQ restricted to S3. It has all these properties. Let me call this a standard contact form. So such a form is called a contact form. And if we look at the data which we have here, then the associated Reb vector field is a vector field generating the Hopf vibration. So a very simple system. And there's, however, more data, namely, what we can look at is, since this form nowhere vanishes, we can look at the kernel of this form lambda. Then this means the lambda does not degenerate on the kernel. So actually, the kernel is a plane field with a symplectic structure on it. So the local geometry of this is, I am given the contact plane, and then transversal to it, I have this Rebbe vector field. So that is the geometry which we have here. And given such a form, it gives me a natural, so given lambda, I get a natural decomposition of the tangent space by the line generated by the vector field plus the contact structure with the restriction of d lambda. So that's a symplectic vector bundle. So that is what you have in the system. So it's more than an arbitrary system. So you have a little bit more structure here. So now, the wonderful thing which happens is the following. So let me first formulate a conjecture which is not complete, is far from being completely solved. Namely, it was a conjecture concerning the question, when can we find a periodic orbit for such a system? Now, by Kuperberg, usually not. However, Alan Weinstein in '78 analyzed some existence result by Podor-Rabinowitz and came up with this condition here. That would be in the three-dimensional case. He has also conjectures in higher dimensions where one can straightforwardly generalize this. So Weinstein conjectured the following. Weinstein 78, every Rebbe vector field has a periodic orbit. So now it turns out that in order to prove this conjecture, the only way known so far is actually to relate this problem with a pseudo-holomorphic curve theory. And trying to do so, of course, was prompted by the successes of pseudo-holomorphic curves in symplectic geometry, which were introduced by Gromov. And then contact manifolds are sort of, symplectic manifolds are brother and sister. I don't know who is who. But nevertheless, in the contact case, the techniques didn't work, and there were some technical difficulties, some technical problems. So I was able to overcome them and then to show that the Weinstein conjecture is true for certain manifolds. Now for this question, more importantly, was once this was established and one had the method, one actually saw that it is possible to derive a theory of surfaces of sections for three-dimensional manifolds. It just comes out. It is intrinsically there for this type of vector field. So there's actually nothing to construct except a big black box. You put in your lambda, you make one choice, you press a button, something comes out. I mean, the difficulty for the mathematician, of course, to construct this black box, but that is basically the picture. Yeah? So there is something coming with a packet which is absolutely not apparent. So let me now show you how you relate this to holomorphic curves. So here at least we have something symplectic. So what we can do is we take a complex multiplication which gives the same orientation like the lambda. So we require this. And then, unfortunately, 3 is an odd number, but 3 plus 1 is even. So we want to extend this. We want to say what we do with the x. So we extend J, we extend it to a J twiddle, which is an almost complex structure. On R cross the 3 manifold. And now here, of course, we have now enough distinguished vectors. Here we have the 1 vector as in the tangent space, and here we have the x. So of course, it's completely natural to say 1 goes to x, goes to -1, and saying having made this choice here, so this is a choice, we can find an R-invariant, almost complex structure, which has the contact planes as complex lines and which pairs the R direction with the vector field direction. So now one is able to write down the equation. And so let me first write down the equation, and then I give you in a particular example what that means, namely in this example here. And then you can immediately detect the richness which you would expect from this theory. So now the problem star is the following. Find a closed Riemannian surface, a finite subset this is the R component, the M component, S without the set into R cross M proper, and then we require to be not constant, which has a property, if I take the tangent map, so I'm going from the surface into the manifold, and then let me call by pi the projection onto the contact plane, so I'm going to the manifold, then I project onto the contact plane along the vector field that this is complex linear. And now we have to, now the J will not appear now, but I tell you in a second. And then you require that if you pull back lambda, you feed in J, then this should be exact. Now this here, this condition here, is equivalent to requiring U twiddle to be, J twiddle holomorph. But that maybe is a better way to write it, because you could even get rid of the A. You just say D of this is 0, and this should give the 0 homology class. J is the complex structure on the surface. Yeah, so you could get rid of the A. A is a dummy character here. Yeah, you could take the D of this equals 0, requires that this is a 0 homology class, and it immediately gives you some new ideas also playing with this term. Why 0 homology class? For example, it could lie in the pullback of the total homology of the surface, which is also a good generalization. So, but let's stick with this one. So this is holomorphic, but now we need some more conditions. Namely, we require that the pullback of the lambda over the punctured surface is finite. So this is a finite energy condition. Then observe the following. If you don't have any punctures, by Stokes' theorem, you can using the equation, you verify immediately that any solution is constant. If you don't have any puncture, any solution is constant. So having a non-constant solution, you must have a puncture. So now, what does such a solution do? So now, let's treat A as what it is. It is not important. Yeah? Let's always look and draw pictures at the U part. So if you have such a solution, for example, if you have the one punctured two sphere, then the image of this looks like this, where this is a periodic orbit. So that means if I run onto the puncture and look at circles around the punctures, these are circles which start to approximate a periodic orbit. So, or more generally, you have a three-puncture torus. It would be looking like this, where these are periodic orbits for the system. On the other hand, if you have a periodic orbit, whose tangent space is generated by x, and x is paired with the r direction, then if you multiply the periodic orbit cross r, you get a holomorphic cylinder. And all the conditions are trivial because, so this here is trivially satisfied. Or maybe it's even better to see in the other formulation, this condition is trivial, it's obviously proper. So if you have a periodic orbit, it gives you such a solution. On the other hand, any punctured Riemann surface solution gives you periodic orbit. So as far as this is concerned, it's completely equivalent, and the Weinstein conjecture would be proving such an object, for example, would be sufficient. Now, of course, you could ask the question, why do I go through all these difficulties? I mean, finding periodic orbits, at least a one-dimensional simple object and so on, you could sit down, try to find it. But the thing is, in general, we know it's not there, and if it is actually there in particular reasons, it is there for deeper reasons. Yeah? And the deeper reasons is that there is a big algebra in the background which actually tells you that it has to be there, and it has to be, and then also, if you have no periodic orbit, it's always easy to create two out of nothing. So there must be some mechanism in the background, and it turns out the right mechanism to capture are actually studying the moduli spaces of such curves, which turn out, if you make it correctly, to be an invariant only of the contact structure, and not of the dynamical system itself. And here, this line of thought will be continued in Eliashberg's talk, when he talks about symplectic field theory, which is precisely concerned with studying, I mean, it goes a little bit beyond that, but with studying this kind of, this equation here, also in higher dimensions, where you can immediately generalize the notion of contact form and so on. So now, I want to pursue a different line there. So there's a lot of algebra in the background which you can do, and you can develop a big machinery doing so. So you could develop a big algebraic machinery actually showing that certain algebraic invariants are non-zero, which tell you that such objects exist, and which would in particular tell there are certain periodic orbits. So now, but we want to do now more in dimension 3. We want to use it to study dynamical systems. So now, this holomorphic curve, of course, these curves there's a wonderful thing in dimension 4, namely 2 plus 2 is 4, and if two holomorphic curves intersect and not identical, they have an isolated intersection, and the intersection number is positive. So there's a lot of rigidity in the problem, and precisely this rigidity is extremely useful in now developing from this a theory of surfaces of sections. So let me just here, in this case, give you an idea how many of such solutions are there in general. So here, if you look, it's a kernel of lambda 0, then this here is a complex line in the tangent space of the sphere, the complex line bundle, the obvious complex line bundle in the tangent space of the 3 sphere. So therefore, here, of course, I could take J as I restricted to psi 0. I just take multiplication by I, and then I look at this equation here. So now, now take C2 without 0, with complex multiplication I here, and take here R cross S3, and take as map Z goes to 1/2 ln Z divided by Z alpha. So the value X is generating the Hopf vibration. So let me take this thing here, and here you put J twiddle. Yeah, so you should just start with the I and then extend it I invariant. So then this here, this is actually a biholomorphic map. So studying holomorphic objects here is the same like studying holomorphic objects here for the usual structure. So then one only has to understand now this properness condition and this condition, and it turns out it singles among all holomorphic maps into this one, it singles out as images the one-dimensional affine algebraic sets take away 0. Yeah? So this equation in this particular case is just whatever you get as an image here comes from affine one-dimensional algebraic sets take away 0. So there are plenty of them, so you get an idea what you have there. And here you have a formulation which now you can deform. For example, you could start putting a function here. Then the kernel is completely the same, But you get a different pairing now in the r and x direction because the wave vector field changes drastically. Because in the wave vector field involves the derivatives of these functions. So it doesn't look, for the naked eye or for the unexperienced listener, it doesn't look as a big change. However, let me tell you that given any Riemannian metric on S2, which restricted to the unit sphere bundle, which is RP3, go to the double covering, which is S3, you get a floor on S3, it's conjugated to a floor of this type. Yeah, so all the geodesics, the double cover geodesic floor on S2 are in there. So it's very general. So, but now you see, if you put a function here and you start with a one function, you get a deformation of an elliptic PDE on an unbounded domain, which might give some headaches. Yeah? But you see, obviously, there's a natural deformation from the affine algebraic situation to, in general, non-integrable situation. And the type of equation will all preserve this richness, but it will not be some algebraic theory. So actually, I'm afraid I need 1.5 hours. So, when did I start? 11? Okay, so now we want to generalize the notion. So I want to show you now that actually studying this object in the images of such solutions, and then looking at foliations of R cross M coming from such things actually will be a natural generalization of the concept of the surface of section. So that's the idea. So let me make a definition. So maybe the good thing is to get inspired. You know? Let's inspire ourselves, indulge ourselves by looking at this example and get a fantastically brilliant idea out of this. Yeah? So what can you get out of this? Yeah? So let's put this lambda 0. So now, so if by some general mechanism we found a plane, yeah? So just pick any plane. So this is now, the plane is here C2. Take a plane C cross C. So now move this plane by moving this constant, but don't make it 0. So we almost have a foliation, except if here's a point 0, we have to remove it. So I take this one also. So now I have a foliation of C2 without 0. So now, this foliation has a property, namely, if I take any of these things and multiply them by a positive real number, I get again one of these sets here. So now, under this deformation here, under this map here where it takes a logarithm, it would correspond, the multiplicative action there would correspond to the additive action. So if I take this foliation here, bring it over there, I have a foliation here consisting of solutions of this equation. Remember, these are affine algebraic sets, which is R invariant. Yeah? That means either I get a new leaf or I get a fixed point. I get the same curve again. So now let's just, so we have a foliation in this particular situation. Is it possible to deform this? So let's make a definition what we are looking for. So let me call this, so I call such surfaces here finite energy surface. So finite energy foliation for m lambda j. So what is given is m and lambda. I make a choice j, a complex multiplication. Finite energy foliation for this is a foliation f of R cross M by images of solutions of, of course, embedded solutions. So let me drop this, of solutions of star with a property that if f belongs to the foliation, then also a plus f belongs to the foliation. Yeah? So that is the notion, yeah, which we get out of this particular trivial situation. So now if you have, so you might have fixed points, you might have fixed points for this R action, but it turns out the fixed points are just cylinders over periodic orbits. So on this space, on this space of leaf, you have the R action. The fixed points are just the fixed points are cylinders over periodic orbits. Then if you have a real surface which is mapped onto something else, there's no periodicity possible. So if a plus f is different from f for some a non-zero, then it's true for all a's. It can never be that a 1 plus f is equals f. A priori might think that something's periodic, of course, but that's not possible. So given that, of course, if you have an R action and you have a set and all the copies are disjoint, then obviously already the projection into the manifold looks already injective, has to be injective. So this already shows you if you have such an object here and you project everything in the manifold, you might maybe not get a foliation, maybe you have to require a little bit more, but you get already the projection of the fixed points would be periodic orbits, and the rest would something project injectively into the manifold, and you would sort of decompose the whole 3 manifold into periodic orbits and sets. So now let me give you the main result. So that is joint work with Wysotsky and Zehnder. And of course, since we didn't completely clean up the field yet, therefore I'm talking about it, so we can give some visions also. So we carried out this in fact, for a particular situation, namely, we're looking for contact forms f times lambda 0 on S3. And we have a complete theory there, but in fact, I don't see any obstructions actually to do it on more general manifolds and so on, except that you have to do it and you need some ideas where to start and develop some general machinery, which I will address if the chairman doesn't stop at me at some point. So now let me assume that this is non-degenerate here. So namely, periodic orbits are non-degenerate in the sense if I take a return map, linearize the Poincare return map, and for the iterates, one is not in the spectrum. So then, under these conditions, the following is true. There exists a finite energy foliation with sphere-like surfaces. That means the models which I'm taking here are just all Riemann spheres. Moreover, a relief has precisely one positive puncture. So here, of course, by the properness assumption here, if I'm going to a puncture, then the R component either goes to plus infinity or minus infinity. Yeah? So I can distinguish positive and negative punctures, and actually what geometrically means, if I have the Riemann surface, it has a natural orientation. Now if I take circles running through a puncture, the image goes to a periodic orbit. Now it might go orientation preservingly, which is positive, or orientation reversingly. The periodic orbits are obviously oriented by the vector field. So it has precisely one positive puncture, but an arbitrary number of negative punctures. We don't know anything in general about the negative punctures. There might be several of them. Then, so that means, the theorem is not finished yet, but let me draw a picture. So the surfaces which occur are this type of surfaces. Where this one here is mapped on, has a positive punctures, and this might be negative punctures. So these are the model of your surfaces. Then, even more. The asymptotic limits, which are, of course, what I mean are the periodic orbits, the asymptotic limits have Konlitzender index 1, 2, or 3. So I will not tell you what Konlitzender index means, but it's completely related to the following problem. If you have a periodic orbit and suppose you have some framing, you can look at the infinitesimal flow nearby, and then you can measure how it winds around. And there, of course, for periodic orbits, natural framings, if you have a periodic orbit, you just take a span in a disk, you pull back the contact structure, take a nowhere vanishing section. Now the contact structure is a normal field to the periodic orbit. So if you have close by orbits, you can see how they wind with respect to this vector field. And then you can see that if you take all the possible windings which you get by taking arbitrarily close initial data, you get an interval, you divide by 2 pi, you look at the change of arguments if you go around, divide by 2 pi, then either it contains an integer, it lies between 2 consecutive integers, and then depending on this, you associate an integer index. So it measures how the stuff twists around. So it's not, but I just want to say that you can be very precise about the dynamics near these periodic orbits. And then, moreover, if f is not in the fixed point set, then this index, then so you have Konlitzender index mu. So each of the punctures, the periodic orbits at the end has a Konlitzender index. Then one can define a global Konlitzender index by taking the sum of the positive punctures minus the sum of the negative punctures, and then the total Konlitzender index minus the Euler characteristic of the closed sphere, which is 2, plus the number of the punctures lies in 1 or 2. So you know enormous amount of things about this, and even this. All the asymptotic limits have minimal periods, and even you can even say the self-linking number of this is -1. So I don't write it down. So you know enormous amounts of things about this. So this is true for a bare set. So here, of course, we have to fix. You have a bare set of J's. Yeah, so this is non-degenerate lambda is given, then it's a bare set of J's that you have such a construction. So now, it turns out that this equation, the system of equation, has a very particular form, namely, you can say something about pi tu of z, which is, of course, if it satisfies the equation, a complex linear map from the tangent space of the punctured surface into the pullback of the contact structure. So this one here is complex linear, and you can show by differentiating this again and using the fact that it's really crucial, this is a projection onto a contact plane, non-integrable. So you can show that if this is not identically 0, then it can only have isolated zeros and with positive index. And there can be only a finite number of them, so they actually stay, there cannot be any accumulation near the punctures. So you can define a total, which I call wind P, a total winding number for the surface. Now, of course, such a number you should be able to read off near the punctures. But near the punctures, you should also be able to read off the Fredholm index for this nonlinear operator. I mean, if you have this nonlinear operator describing your curves, and then if you linearize, you have an elliptic operator on unbounded domain, it turns out the Fredholm should have an index. So now it turns out that you have this a priori inequality. It turns out that this one here, which I wrote down, index of u, or index of f, whatever. So let me write index of f. And u would be the map where this is the image of. Yeah? So this here is actually the Fredholm index. It describes the index of f lying in R cross M. So you have the R action, which gives 1 dimension. If the index is 2, it means there's also a geometric moving in place. And if the index is 1, it's sort of a rigid surface, and the only moving is the R action. So then it turns out that you have this a priori inequality. The wind P number is less or equal to the index of u. So before I get overexcited and write some new inequality, which would bring me further than I get here. So minus 2 plus the number of punctures of index 2. Actually, in general, the number of punctures of even index. So, now it turns out that these conditions here control that there can be at most one of these guys. Then this is 2 at most. We have 0 here, then we have a 1 here, and here's a 2. Sorry, there's a 2. So the worst possible case which we get out here is 1 is greater or equal to this, so this has to be 0. If this is 0, what does that mean? This means pi tu is complex linear, so tu has maximum rank, and it's transversal to the flow. So the Freedom index actually controls this. So now you take all these surfaces and project them in the manifold. And that is your global system of surface of section. So in particular, if you start with the Riemannian metric on S2, go to the double covering, go there, it's applicable. There's a global system of sections which are of this type here. So now, let me just draw you some pictures. So you start with a round sphere Hopf vibration, which you understand, and you could take this very trivial foliation coming from these parallel planes. Now you start deforming this into a convex set. Now convex, here is a non-trivial example of convexity in the symplectic manifold. It turns out, if you have a convex set in R4, strictly convex set, then the Konitz-Zehnder indices, which can occur a priori greater or equal to 3. So there are only this type of surfaces here. So if you have a convex set in a symplectic manifold, the winding of a dynamical system around it, it always winds stronger than 2 pi for canonical framing around all the periodic orbits. So then what we get is such a foliation, but only with this type of surfaces. So let me view S3 as R3 with a point at infinity, and let me assume that everything is symmetric to the blackboard, which is R2. So here I have a periodic orbit coming out of the blackboard, and this has its trace here. So now my foliation down there, these are the traces of the foliation, and if I have here just 3, then the total Konitz index would be 3, minus 2 is 1, plus 1 puncture is 2, lies in a 2-dimensional family, R action out is 1-dimensional, this lies in a 1-dimensional family. And then, of course, it cannot degenerate because there is a mechanism how a surface can degenerate, and what you get is an open book decomposition of R3 transversal to the flow. You fix one of the surfaces and take the return map. You can also, the information about the Konitz-Zehnder index at the orbit, at this periodic orbits tell you that they actually wind around. It's impossible that if for the time they just never go around. They have to go around with a certain speed through all the piles of surface if they stay around such a periodic orbit for a long time. So now you fix one of the surface, you have a global surface of section, and then it must, this surface here, this return map is area preserving for the form d lambda to the surface. Then d lambda integrated by Stokes' theorem is lambda over the periodic orbit, but this is a Rebbe vector field lambda and it's equal to 1, so the area is even precisely the period of this periodic orbit. So now you can, if you have an open disk with finite area and an area-preserving return map, it must have a fixed point by Brouwer's translation theorem. So we have this situation, the spanning orbit and this one. Now remove these two things and you get a return map of an open annulus, area-preserving. Then by result of Franks, if it has periodic points, it has infinitely many. So we get in this case that we have either precisely 2 geometrically distinct periodic orbits or infinitely many. And in fact, in this particular case, we don't even need a non-degeneracy assumption. So in this case, we actually prove this in general, also with Wysowski and Zehnder. So now, importance of convexity. Now we start with convexity, and so we start with lambda, and we change f from 1. So if we stay close to 1, the surface, I can realize the surface as lying in C2 by just deforming it. I can visualize it. Yeah? I just take a point of the sphere and stretch it actually by square root of f. So I get an energy surface in R4 and or in C2. One can actually show that the dynamics on this is actually conjugated to the Reb dynamics there. So now we start deforming it more widely. Go to any f. then suddenly certain accidents arise, namely, out of nothing, you can create a pair of periodic orbits, an elliptic and hyperbolic one. So let me just draw to you the simplest possible accident which can happen. Namely, we could get suddenly in hyperbolic, so we create this guys here. And let me draw, and there's of course, and this theorem will give a foliation which would look like this. So this would be, in fact, rigid surfaces. So this would be surfaces which coming with index 1, would be one here, and here. This is a set of rigid surfaces. And then the Condorcet index would be 3 here, 2 here, 3 here. So it would be the sort of simplest accident which can happen when I start deforming. And then I would, then when I try to continue my finite energy foliation for the round sphere, then there is some kind of a homotopy invariance like in Floer theory, but also considering higher dimensional components. And that is sort of how you deform the whole complex. And you get this picture. So I implanted this ball here with this particular dynamics. Now this here, Condorcet index 2, precisely means hyperbolic, in particular means implies hyperbolic and orientable, stable, unstable manifold. So now let me tell you why now the general result, the corollary of this result is the following. Assume, which is also a Baire-type assumption on F, so there's a Baire set of Fs. Assume not only that lambda is non-degenerate, so the wave vector field, but also assume that the stable, unstable manifold of hyperbolic orbits intersect transversally. This is true for a Baire set of Fs. So let me now tell you that one of the two things happens. Either, in general, there's a global disk-like surface of section, in which case we have either precisely two geometrically distinct periodic orbits or infinitely many, or there's a Bernoulli shift. Yeah, so that means in this case we have also infinitely many, but the transversality assumption, so the general case is either precisely two periodic orbits or infinitely many, which also gives a nice point of view for the geodesic problem. Double covered has at least 3 periodic orbits, yeah, by Lusternick Schneer one, yeah, and 3 means infinitely many, yeah, by this result. So now one can study how the stable and unstable manifold of the hyperbolic orbit are situated in the space. And they're precisely situated like this. So this here is the stable manifold, and here is the unstable manifold. So I wonder if when do I have to stop? So what? A minute ago, okay, but that's not too bad, yeah, given the previous example. So, let me just wrap up the whole thing. I think it's a nice idea here. So now, the stable manifold here intersects out of the leaves, which are close by here, intersects here, cuts out a disk. Yeah? So let me draw this picture. So this surface here is this one, and the unstable manifold cuts out a disk. Now this unstable manifold, of course, continues here, but it's always transversal to the foliation. So this cutout sphere here, or this cutout disk, let's take just the disk. The disk goes continuous and continuous. So now what happens to the boundary of the disk? Now if the boundary of the disk has an orbit on it, which is just the unstable manifold, is being eaten by the stable manifold, I have a homoclinic orbit, so I have a Bernoulli shift. Yeah? So I wouldn't have a Bernoulli shift if this is not going to happen. So now this moves on, and suppose these things here are never being eaten by the stable manifold, or this one. But what happens? Yeah, but then they go through it, and they always avoid, for example, it cannot happen that part goes through here and part goes through here, of this S1 here, because if part goes through here and part goes through here, intermediate value theorem, some has to go on the stable manifold. So it also goes right or left. And let's assume there's no homoclinic orbit, so this happens for all times. But now you see there are only a finite number of families, namely there is here this one-dimensional family. Here's a one-dimensional family, and there are a finite number of rigid surfaces. So now the thing moves, and then there has to be a family which is infinitely many often hit. And if you have a one-dimensional family and hit one of the surfaces infinitely many often, you hit all the others. So it doesn't matter. So there is one surface which is infinitely many hit. So now suppose this is a one. So now you cannot intersect it by the uniqueness of the initial value problem because you know the backward story, it goes in here. So if you hit the same surface, you must get again a disk of the same area but disjoint, and again a new disk of the same area, but that is impossible because the disk has finite area. So there has to be, in this case, a homoclinic order. And the argument goes completely through in general. Yeah? It's a little bit more. No, this is what I assumed. I assumed this. For a bare set of F, that's true. So now, in the general foliation case, you can do the same argument, but what you would show, either you get a homoclinic or you get a heteroclinic orbit. But then you start with a new one again, and continue, and so on, and ultimately, because there are only finite number of spanning orbits, you must have a heteroclinic loop. And then by transversality, you get also homoclinic. So then you have a Bernoulli shift in the system. So now, so in this case, if you have a Bernoulli shift, you have infinitely many periodic orbits, so the results too are infinitely many. Now, I think this is actually true without any assumptions. So for any contact form of this type, F times lambda 0, I think there are precisely two periodic orbits or infinitely many geometrically distinct orbits. I think let's assume is the right conjecture. Then, what should be investigated is what happens on which more general manifolds can I make this construction. It seems to be definitely true that if I have a manifold, I can make a construction with some additional assumptions, like finding, I need more rigidity in my problem, you know, like some index assumptions, so on, that if you have such a filling or foliation for one contact form, you have it for any other contact form given the same contact structure. So I think having something of this type is a property of a contact form and not of a contact structure. You know? So it deals with this whole family of systems simultaneously. Then, if you make a connected sum, I think it's well behaved under connected sums. If you have two things having this property, then I think the connected sum has. And the other is if you make a surgery along a Legendre knot, I don't know. But maybe it depends on the framing or what. Maybe you have such a property as well. So ultimately, what you should be able is to generate a whole class of dynamical systems for which you have this very helpful tool for doing dynamics. And also, there's another side to the story, namely doing geometry, namely understanding three manifolds, and that connects with what Elias will be talking about. He will talk about a symplectic field theory, which I think will be particularly strong in dimension 3, because then this type of things would be things that would be measured, at least part of the measure in such a theory. Thank you very much. I'm finished.